Good morning, guys. Hello. Small crowd. I'm sure you're all coming. Everyone else is coming. Um, Maybe you're watching the inauguration. Maybe you're just waking up. That's all good. Um, yeah, we've made it halfway through the week, and I hope. Good morning, Robin. I hope today is better than yesterday. That's kind of always the hope, right? Um, yesterday I realized that I hadn't eaten all day until after class, and then it made sense why I had kind of a headache. So if I said anything kind of weird yesterday, y'all, yeah, um, yeah, I realized it after class. Actually, after a meeting after class, I was like, oh, oops. Good morning, Andrea. Good morning, Noah. Yeah, so as always, remember to have something to eat, some breakfast, something to drink. Today's drink is a mini coffee that I made at here at my house, but it's just a little bit of coffee and some water. Good morning, Keon, to everyone too. Yeah, I think I definitely want to be, more alert and focused than yesterday. We have a chapter to finish. Good morning, Mehmet. And we have chapter 8 to finish, start and finish. And again, it's very doable. The way that we're going to proceed through every chapter, it's very doable. Good morning, Daniela and Saja and Luis. Good morning to you all. Okay, I think we have at least more than 15 of you now, and we'll get a few more as we come in. I wanted to just mention one thing about internet issues because I know we're all having them right now. And last night I was on a Zoom meeting and I couldn't even speak. I just had to chat because my internet was going in and out. So, if anything does happen, I don't know what I have in my mouth. If anything does happen, just hold tight. I'll always come back in. And same for you guys. Have some patience with your internet issues right now because we're all going through it. So know that the recording will always be there. Okay. I think. Okay. We did talk a little bit yesterday about everyone having power issues, and I know some of you on the call today and yesterday were having those issues. So I hope for all of you it's better. I actually didn't. I know the winds were really strong yesterday, but I never stepped outside, so I didn't feel it. But I know, right?
It
Working from
wasn't as
home.
bad as they said.
It is as bad or it's
It
not?
wasn't.
It wasn't?
Yeah. It was like dusty and pretty windy, but like it wasn't as bad as they said.
Oh
Oh,
no, no, no. You weren't where I was. It was
yeah,
nutty. It was like 70-degree winds. It was like hurricanes. It was crazy.
yeah. Yeah, I think it definitely depends on your area, but from the news coverage that I saw, it looked really strong. But again, I didn't step outside in downtown, so I don't know. I don't know. Oh yeah, some of you. Oh yeah, for some of you, it really was all over. And I'll remind you that because of our Zoom class, you guys are from all over LA County, not so much centered around downtown LA, which is kind of what I'm used to. Um, but no, you guys are all over LA County. So, yeah, the smoke, the lights flickering. Yeah. So, mostly take care of yourselves and have some patience, right, with that, with internet and everything. Yeah, Little Armenia, Thai Town. Kian, that's my most favorite Thai restaurant is in Thai Town off of Wilton. I'll have to tell
Oh,
you.
which one? Tarang?
That's right.
Tarang, that's where I
It's
live.
called
That's my
Torang.
place.
Oh,
Tarang, yeah.
so stay inside at night. But yeah, that's. I told you guys I did work in Thailand, right? Yeah, and so when I was young, my family always lived in the like Pico Union kind of Crenshaw area of LA, and Torang would be open until 5 a.m. So my dad and my mom my dad and my mom would go there, and it became like a normal place for us. Fast forward many years later, I go to do research in Thailand, and I eat only Thai food for like 6 months, and I come back, and of all the places I've tried, Torong is still my favorite. So anyone in the kind of Hollywood area, it's open until 5 a.m., 5 to 5.
Well, not anymore, but unfortunately.
Yeah.
But I think, but before they closed, they were open till 3 still. So, which is
That's right.
amazing.
In the past, it was 5 to 5, and then you're right, it did change like 5 to 3. But late at night, a good place to be open. At the time, also cash only. Now, any app you can order from. Yeah, still cash only. Man, one day maybe near the end of the winter, we can have a full LA session, and we can talk about all the good spots in LA too. Yeah. Or a field trip, man. I wish. Yeah. We'll talk about it soon. Yeah, you guys know some of these places. You know what I like to do, and I swear this isn't like a physics segue thing, but I really do like to see science all over the city. And if you ever walk around downtown LA, especially in the library, all along the outer walls of the library, there's physics and science, like in the wall carvings. You can walk by and see Schrodinger's equation, and it's so cool to just walk by on the sidewalk and then see science everywhere you go. So, and the cranes over downtown LA are my favorite. Oh, I love seeing cranes. Yeah, if you take engineering 101, that's the cantilever that we built. That's basically modeling after a crane. And you see them everywhere, especially downtown. Okay, I think we are ready to finish chapter 7. Yeah. Oh yeah, San Pedro has a whole bunch too. I go that way a lot, Owen. I like to walk along by the Korean Bell and all that area too. I love it. Yeah. Okay, we will finish chapter 7, and then we will start chapter 8, and then somewhere along the line, we'll take a break, and towards the end of the class, we'll go over the lab. I hope you got a chance to read it. I'm going to go through the intro of it and then a few of the directions for it, and then we'll be done for today. I think 12:30 on the dot, maybe sooner, who knows? Okay, let me set up my screen, and I will take us to chapter 7. Let me move you guys back around. And let's see, where do I want to finish with? We're going to start there. Okay, so let me share my screen and then bring us to the starting screen. Okay. Okay, let me move you guys around. So I can still see all of you and your boxes, including your emojis that you use, reactions. And I've just moved around my chat screen, so now I can see the chat completely too. Okay, and I hope you can all see my screen too. Let me take out my little pen. So where we finished yesterday was talking about creating this complete picture of what is happening in a situation using physics. And up until now, we've been really good about describing motion using kinematic equations and Newton's laws of motion. And our new concept from this week is that sometimes you cannot describe a situation purely by motion that you can see with your eyes. You need to also use something like energy to describe what's happening. Energy, we're going to learn, is the capacity to do work, being able to do some sort of work. And when you do work, what is actually happening is that you're displacing an object due to some force you're applying at some angle, and that is work. And yesterday after class and at night, I was thinking a lot about our conversation with that box, right? And the displacement going to the right and our force going to the left. And I know we got over that hump yesterday, but I did think about it some more, and I wanted to make sure that we know kind of the order of things. And when you describe work, the displacement and the force are the things that come first. So work is a result of this displacement and the force. You can't really describe the displacement going one way and the force going the other way and saying that's going to give you, that doesn't physically happen. When the two are looked at together, the result of that is a capacity to have some sort of energy. And that is the work that we have. So the definition that we came up with is that the magnitude of work is the magnitude of force times that displacement times the angle cosine theta. And this cosine theta is really what will give us the direction of the direction or the sign of the value of work. Notice that the value of work is not a vector. This is a scalar. And so because of this definition, we can also come up with a mathematical definition of this product, which is the scalar dot product. It's called the scalar product because it results in a scalar. Two vectors result in a scalar, or we call it the dot product. And this is our dot right there too. So yesterday we finished with practicing two problems with the dot product. And this very much gives us, because of this displacement here and this very exact force here, it very much gives us an overall view of what's happening, what is the work for the situation. As physicists, always, we want to go into an instantaneous view. What is happening at any moment, and how do we establish the work at any moment in time? So here we put on our calculus hats and we go on to our more exact definition of work. And here it is. So when work is done by a varying force, if we wanted to look at an exact moment in time, just like we did before, we could sum up all of the moments or reduce that time to as close to zero as possible, and then sum up all of those moments in time. So for example, when the force is not constant and the force will vary in some way, for any small displacement, we reduce it to as close to zero as possible. Any small displacement will give you an approximation of work. If we then sum up all of those small displacements, we can get a larger view for some interval, some displacement interval. Now, if we take those small displacements and take that displacement as close to zero as possible, and that's what you see here, where we start to cut up these pieces of X to these small segments, and we limit that displacement as close to zero as possible, and then we add them all up. That's what the sum is. If we add them all up, what we're actually physically doing is looking at the physical area under the curve of this graph. And in math and in calculus, that area under the curve, if you limit that displacement to zero, is our integral, or you guys know it as our antiderivative. I think that's what you guys call it, right? Antiderivative, something like that.
We called it integral in my Calc 1 class.
Okay, I thought that maybe the intro to the integral is the antiderivative, but we don't use the word antiderivative, so we use integral. So that's yeah, we'll go with that. And notice again the opposite things that the integral is doing versus a derivative, right? A derivative is giving us a very exact moment in time, right? At this moment, what is the slope of the curve? That is your dx dt. But for the integral, we're taking an initial moment to a final moment, so some entire span here from this initial moment to this final moment, and we're adding up every single one of those things. Yeah, it is also an antiderivative. I know someone out there has heard that too. So when you're doing this, you have two ways of solving this. You can take an integral of a curve or an equation that you're given, or if the curve is a nice symmetrical curve, you could just use geometry and figure out what is the area under the curve. So the work now is defined as the integral from the initial to final position of f of x as it varies in that displacement, right? As the force varies in that displacement. And this work is equivalent to the area under the curve. So let's try, I think the integral of any basic equation like an exponent or a natural log or e, right? You guys are okay with that, and that's really as far as I think I'm ever going to go in these integrals. So as long as you can do the integral of an exponent or natural log or e, I think you should be okay. Maybe even sine and cosine. Yeah. So let's try a symmetrical curve. Okay. Here you have a force that's acting on a particle, and of course it's going to vary with x as shown in the figure. Calculate the work done by the force on the particle as it moves from x equals 0 to x equals 6 meters. So notice,
With sine and cosine, is it like the area above the curve or below the curve?
You mean the integral?
Yeah, like the work done, is that the area above or the area below?
No matter what function you use, the work is always the area underneath the curve.
Okay.
Yeah. Yeah, and Owen brings up a good one because Owen brings up a nice whole definition, because sometimes you're going to have a curve that looks like this, right? And here you're going to say the area under the curve, but it's always a whole definition is the area between the curve and the x-axis. So this would be the area. So no matter what mathematical function you use, work is defined as the area under the curve if this curve is described by a force varying with x. And so here we have a nice straight line. So without, and we're not given any equation in the problem. So this is your clue to use geometry. Now, I did have some people in the past, a very small percentage of people that start making an equation, right? A y equals mx plus b, and you go through that whole process. You can do that, but that is an indirect method to solve this, and it's not the most efficient, right? Oh, and Mehmet says, do we take the absolute value of the area under the x-axis? No, you take you're gonna sum everything up. Yeah.
So it's not like the displacement, like where you negate the thing below.
That's right. It's not. Yeah. So no, and so just for Mehmet's question, no, I don't think you take the absolute value.
Yeah, that's the same as that, like negating the below, I think.
Yeah. So you sum everything up for whatever value you get. So let's try with this one and see what we get. So I think the obvious way here is that you would see a rectangle and a triangle. And so we know those areas. And for the first one, then we can take the work done from A to B as the area of the rectangle, 5 newtons times 4 meters. So this is your 5 newtons, right? Newtons times 4 meters. And so you get 20 joules here. So in this area, 20 joules of work is done. Notice that even when you multiply the geometry, length times width, the unit stays, and the unit, because the curve is f of x versus x in newtons versus meters, the units will always match. And that's something that should always be correct or be carried through your calculation. So for the triangle, we can do half base times height here. And you have, what did they do? They did the height, 5 newtons. And half of the base from 4 to 6 is 2. So 5 newtons times 2 meters and times 1/2. So 1/2 base times height. And then we get 5 joules there, right? So this is 5 joules. So in totality, then, the work from A to C is the sum of the work of all of the area under the graph, 25 joules. So mostly you're going to see these type of problems. Could you use the integral? If you have an equation, Luis, you can use the integral. If you don't have an equation and you want to go through the process of creating an equation, you can. And you'll, I think at least one problem in the homework is assigned that way, so you'll get some practice doing that. But let me show you guys what is the real purpose of us starting with work and us going through the definition of work. Work is going to give us the definition of looking at all the other and at several other energies. Notice when we talk about work, we always talk about a force and a displacement of some sort. So a displacement has to happen. A change in position has to happen for us to have work. So one of the most common scenarios to study this change in displacement is a spring, because a spring, you apply a force and you change its displacement. And you can apply a force in different ways and get a displacement also in different directions. And that study is going to take us into kinetic energy and potential energy. So here it goes. We understand work and we can use the integral, we can also use the area, but we're going to take this study of work and apply it to a spring, because here is a really good example of where this force varies with position. So let's start at system B here. And this derivation, you don't need to know it by memory. I'd rather you more follow along. So let's start at position B here, where the spring is in its natural state and the block here is sitting at what we call 0. This is our 0 position, right? So here, natural state, there's no displacement, there's no force. This is its natural state. Now, if we move up to position A, and looking at position A, now we've stretched out the spring, right? We stretched out the spring and we've caused some displacement, and the block is sitting here. If I were to let go of this, the force of the spring would then pull the block to the left. We displace to the right, but the force of the spring will pull it back to the left, right? So here, there's some sort of a relationship, opposite relationship. And we have that situation. Now we go back to our natural state and we're sitting again at the natural state. Now we go to position C. From the natural state, now we push the block in with some force and we compress the spring. So we've pushed and we have now some displacement. Maybe you can call this some negative X, right? We're moving in some negative X. And if we were to let go of the block at this position where it now has it's holding on to some force, it would leap forward to the right, right? So the force of the spring then on this block would be to the right, opposite in direction to the displacement. So what we see here is that there's some opposite directional relationship here between the movement and the force of the spring. This brings us to something that we call Hooke's law, which will help us derive kinetic energy. So the force that's required then to stretch or compress the spring is proportional to the amount of stretch or compression in X. So if you apply some force, you will get some compression or stretch. If you hold on, Randy. If you increase the force and you increase the force to stretch or compress the spring, then you will also increase the amount of X that you get. What's your comment?
Does that mean that, like, the more you stretch, the more force that it takes to stretch it?
Yes.
Okay.
But chronologically, the other way around. The more force you apply, the more you'll stretch it.
But you're not saying that, like, when you have this spring all the way over at max, it's most difficult to keep there?
That's not the force that we are looking at. We're looking at that's T equals negative time. We're looking at once it's compressed or stretched, now what is the force of the spring when we let go of the block? So we're not looking at the force that we're applying on the block. We are looking at what is the force that the spring is going to use to get back to its natural state. That force of the spring is proportional to the amount of displacement that we caused.
Okay. Is like that amount of like work That's work, right? Is that amount of like
It is an amount of work, yeah.
is that amount of work the same for like the first half of the delta x as it is for the last half of the delta x? Like
So when you say when you say first half, I think you mean like stretching, and the second half you mean compressing.
Like cut that delta x there in half. Is it the same for the first half as it is the second half? Like, is it the same to get from the 0 to the half as it is to get from half to, that line, the dotted line?
They move proportionally to each other. The more force you place, the more you will displace.
I guess I'm not asking about the displacement, but I'm asking about, like, is the force constant throughout the entire system? Like, does it increase as you get closer to 0, or does it, like, that's what I'm wondering.
So what I'm telling you is that it increases with displacement. So if your x is 5, your force will be proportional to 5. If your x is 10, your force will be proportional to 10.
So is the force, so if you have some 0 to 10, right? And from 0 to 5, is it the exact same amount as it is from 5 to 10?
0 to 5 is not the same as 5 to 10. So I'm going to show you mathematically what this looks like, because I think you're jumping ahead without seeing the steps to get there. So the force required.
Could I say something real quick?
Sure.
I'm sorry. So Randy, if you look at the bottom figure, see that's the shaded figure is the force, or I mean the work, right? So
Yeah.
it's more work as you compress
Yeah.
it, or it's proportionally more, but it's
So,
not
like,
the same.
the thing that was confusing me is I see a K, so I'm thinking that.
So guys, you see a K, but I haven't mentioned a K. So let's take a moment and let me teach. Let's continue with this. So this force required, again, is proportional to this x. What this means is that there is some proportionality constant that exists. This is what we call Hooke's law. Hooke's law says that the spring force is proportional to that displacement x, with this inclusion of a factor that's this k value. There's also this negative value because we see that this change in x is going to be the opposite direction as the force on the spring. So this will give us our opposite direction there. Now, directionally in vector notation, you're going to see that this can be written with the magnitude and a direction. So the force of the spring, it's a force like any other force, so it's a vector. The magnitude will just be the force of the spring, and the direction in this case will be an I hat. And our magnitude then for the force of the spring is this negative kx. In the direction of I. So what does this K tell us? The K tells us this K is, again, a positive constant. It's known as a spring constant or a force constant when you talk about Hooke's law. For any stiff spring, you're going to have a larger value of K. So for something that's really hard to compress, like a hard spring, a stiff spring, that value of K is going to be harder, which means it's going to be larger. Yes, more material science, which means that our force is going to be larger. So depending on the material and depending on the displacement, your force will change with that, but it's going to change in a proportional way. So they're just like this graph shows you down here, where we plot the force of the spring versus the x, we have a linear relationship that exists here. And again, this linear relationship, as you displace, the force of the spring is also going to be greater coming back at you, or extending back to where it wants to be. So for a stiff spring, of course, you're going to have a large K value. And for a soft spring, then you're going to have a really small K value. Think of something like a slinky, right? A slinky is really easy to move, and you don't have to apply a lot of force to displace it. And then the force that the slinky pushes back to get back to its natural state is also very low, not too much. And that, again, is proportional to that K value and to the X value. And of course, this force of spring is going to be in newtons. because the force is in newtons. And so our K value is going to be in newtons per meter. And having this in Newton per meter and the meter in X will cancel out and give us the unit of newtons in force. Questions, comments? So this very much is material science, right? Oh, I see a thumbs up, thank you. This very much is material science. This K value is very much like our coefficient of friction, where we have a table, and depending on the material, you can use any material and figure out what is that factor, that number that everything is going to increase by. And this is really, to me, that every time we see these factors, you're going to see them a lot, coefficient of friction, and in Physics 102, you'll see them a lot too. These numbers are really our way of connecting the physics to the math, because for us to say that something is stiffer or softer, we need to mathematically add a value there. And the relationship sometimes is just a number, you know, for every 5, you increase 10. So it goes 5, 10, 10, 20, 15, 30. That relationship is that coefficient of K there.
Is that coefficient like related to like materials hardness?
Yeah, that's exactly what it's related to. It'll tell you, so not directly the hardness, and only because I'm thinking of like a formal definition of hardness, but it is very much related to how the bonds are, how strong the bonds are in a material, and how much are they able to stretch, right? The electrical force that's holding them. What's the range of us being able to pull them and push them without them breaking? A very large K, of course, is going to be really stiff. If something is really stiff, it's not going to stretch. It's going to be brittle and break right away instead.
So like a really hard metal that could scratch a soft metal is going to have like a proportional K value to that scratch. Like,
yeah, that's right. And then, oh yeah, okay, so it says a diamond spring would have an insane K value. Yeah, imagine, guys, how easy is it to stretch a diamond? Not very. I think you'd have to put it in a very specific geometrical configuration for it to even be allowed to stretch, but it'd be interesting to see. And then Andrea says Newton per meter would be joules. Oh, and joules or Newton meter. Thank you, Owen. Oh, thank you, Noah, also out there. Okay, so Hooke's law is very important to know and see, and you're going to see a lot of it in statics especially, and in your dynamics classes if you keep moving forward in those engineering classes. We want to use the definition of work here and Hooke's law to come up with our definition of kinetic energy. The reason we use Hooke's law is because this force is varying with position. As the position increases, the force increases. As the position decreases, the force will decrease too. So this is a place where we would use our integrals. So here is the derivation that chapter 7 is all about. Let me put a quick timer on and get us there. Okay, so we just saw on the last slide that the force that the spring exerts onto the block will be proportional to how much it moves, right? Its final position. So we can take our integral definition of work and use this force. Remember that work is equal to F dot dr. You probably haven't seen it with that D, but it's the same as the delta, but now we're looking at instantaneous. So that's the D as in a derivative of R. Okay, so here let's go through the integral now. So now we can take the integral of how this force varies with displacement. And here's the work done on the spring, the integral of F dot dr, which is what you saw on the last page. And I'm just gonna quickly remind you of it so that we don't get lost here. This is what we're doing. This is magnitude, and we're going to start in vector form and get out of that vector form as you properly need to. Okay, so now we're going to write force and dr in its magnitude and vector form. So the force vector for a spring is negative kx I hat And dr, the magnitude of one slot in the displacement is just dx. And you want to convince yourself with that using our graph. And I'm going to show you it really quickly. So here is all of dr, right? All of dr, and one unit of this dr is some displacement of x, so dx. So we can write the vector dr then as dx I hat. And so we take our dot product of I dot I, and we know I dot I is equal to 1. So now our vectors go away. Oh.
What does the arrow stand for?
What is the what?
Is that the position vector?
dr? Yeah.
Oh, okay.
Yeah. This is like, that's the exact, and this is like our, like average. This would be like our average, and this is our more instantaneous. Okay, so I dot I is equal to 1. So we're left with negative kx dx. And look what we've done. Now we can actually integrate because our what is this called? The factor, the integrating factor, that thing. The what?
I feel like I heard differential or something.
Yeah, something like that. That now matches, right? It matches, and now we can perform the integration. So we are going from x initial to x final. And in this situation, x initial to x final here, you really want to make sure where you're going to start at. We started with a compressed spring. The compressed spring was moved to the negative x, right? So we started here, and this was our delta x. This was our delta x here. Oh my God. And so our initial position is the maximum point at which we compress that spring. So we compress the spring, and that's our initial position. And our final position after the force of the spring now pushes the block is back at our resting place. So we can replace those positions in the integral now. So x final equals 0 and x initial equals negative x max. And now we can perform this derivative. I mean, this integral, negative kx. Owen is asking, so r is the same as dxi because the position vector is a change in the x direction. That's correct. We're doing everything along the horizontal, and so we can rewrite that. If you were along a vertical, dr would be dy. Then we wouldn't be able to integrate, right? But we'd have to flip over the whole situation. Yes, so dx is because we're in the horizontal. Okay, so if you don't remember how to do the integral of negative kx, you know, negative k is the constant that comes out. You're really just doing an integral of x, and this is the equation for that. So what's here? A 1, so this becomes a 2, and n equals 1, so this becomes a 2 also. So we have x squared over 2, and then you do final minus initial, where this is final minus initial. And when you do that, the negative will become a positive. I'd like you guys to do that step on your own, but I am going to write it out at least so that you can see.
The negative k doesn't like come to the outside of that little integral symbol?
It does come out. You just have to do all the steps out, but it does come out. This is just them showing you the solution. This is negative xn max. So this is what you come up with, right? So first, this negative, these two negatives become a positive. And the first x squared here is a 0. So this whole thing goes away to 0. And these two become a positive. So you're left with 1/2 kx squared max, because this is going to go in there. And so I just did it for you, but this is the type of thing you want to either start to recognize quickly or practice it after class just to confirm that that's the answer.
Why does that go to 0?
Because this is 0.
Oh,
0.
okay.
Yeah. They're showing you really quickly, but if you take the steps to do it, you will see that their math matches, and you should confirm for yourself. So this 0 plugs into x squared. Negative xm plugs into x squared here. The negative x squared becomes a positive. These two negatives become a positive, and so we're left with that solution that you see up there. And let me circle that. we're left with this. Okay, so now with this, we can pull that to the side and say that the work done on a spring then is 1/2 kx squared, where you maximize your push, whatever that push would be. If we want to write the full integral of what we just did, here it is. The work done on the spring is the integral from the final to initial position of negative kx dx. And this is your solution. And notice that all they did was distribute the negative out without putting in the 0. So this is, what's that called? Not explicit. Like when you don't put in the variables of initial and final. I don't know what they call that in
implicit differentiation.
Indefinite?
Or indefinite or implicit. Yeah, indefinite. Let's go with that one. Yeah, so this is the indefinite integral. And here, this is the same thing as what we just did up here in the negative 1/2 kx minus 1/2 kx squared, where this minus becomes positive, this minus becomes positive, and then you're still left with this negative. And so you can flip the order of these, and that's why initial comes before final here. And Isla says this equation of work is only for a spring, correct? Yeah, this is for a spring, and it's very specific to that, but we're going to tie this in pretty much to the idea of motion. Yeah, it looks familiar. I'm really glad you said that, Isla, because it's about to look, I hope, really familiar to you guys, to an equation that we see. This is the foundation, though, that shows us that with some motion, there will be some proportional amount of work that has been done. With some amount of motion, some amount of change of x, there is some amount of work that's being done. Okay, so here is now our definition for energy. So we can take our definition of work and look at our total sum, where now we could look at any external force that's being applied, not just the, Saja, yes, this was in Calc 2, good, I'm glad you're about to see it. Oh, and then isn't the 0 where the spring attaches to the box? No, because that is the negative time. That is us applying a force with our hand. We are looking at the situation where it's already been compressed or stretched, because we're only going to study, in chapter 8, we'll see that us applying a force is an external force.
I'm sorry, one more question. Isn't the 0 where like the spring would be under no force? Then?
If the situation is where we haven't applied a force, yes, but the situation is the force of the spring. We are solely studying the force of the spring. Yeah, and this is kind of to what Randy's point was also. So you want to just stay focused on the force of the spring after we've applied our hand force to stretch it or compress it. Yeah, so the initial situation is when it's compressed here. And this is really specific because we need to be very clear of when is the timing of what it is we're studying. You'll see that in chapter 8 too. Okay, so we can take what we've just done and apply it to any force that's being applied, right? Any force that's being applied. And we can start with our definition of work again. And now we can extend that to any external force that's being applied to this object. So we can say here that this external work that's being done on this object will be the integral from the initial to final position of the sum of all the forces on some really small displacement, whatever that force will be. Now we can apply this to any external force, right? And let's say we use Newton's second law for F equals ma. So now we have F equals ma times dx. Okay, and we want to study very precisely what is the change in position. And so we write the acceleration as dv dt. And notice here that we still don't have anything that we could differentiate, right? So we're going to take one more step and we're going to write this, we're going to recombine this. Does anyone recognize this?
Velocity.
Yeah, it's our velocity. So we're going to recombine that, write it as velocity, and bring over the dv. And now we have something that we can differentiate or integrate, right? Because that matches. And so work this work due to any external force is now equivalent to mass times velocity over some displacement of v. Yeah, what is the big C? Big C slash? I don't know. So here, just by rearranging these, which we're allowed to do, we can get the integral in the form that we need to differentiate it. So mv dv. Now you can actually integrate this, right? Mass is a constant. We pull the mass out and we take the integral of just v. And the integral of just v will give us 1/2 mv squared. And we then apply that from the final to the initial velocity. And we have 1/2 mv squared final minus 1/2 mv initial squared. The difference of this, right? We know very well now that we could write this as the change in the work due to some external force. And that is the definition of kinetic energy. This kinetic energy then is defined as 1/2 mv squared. And when we say defined as, we mean that the kinetic energy will only happen if there is some sort of motion, some sort of change in position over time. And the relationship, the proportionality that exists here is the factor 1/2, and then the velocity is squared. So 1/2 times the mass itself, v squared. So we could write then this work is actually the final kinetic energy minus the initial kinetic energy is equal to this change in kinetic energy. Ah, yeah. Yeah, you probably did see this in chemistry, but it's physics. And so the reason we really study Hooke's law is because this allows us to see the derivation of getting close to that kinetic energy. Then we apply the Hooke's law, we apply it to any external force, not the spring force only, and we can get a formal definition for any object due to any force that's acting on it. And so then our formal definition then for kinetic energy comes from the work kinetic energy theorem. This external work is equal to the difference of the final minus kinetic energy. And here's your formal definition. When work is done on a system and the only change in the system is the speed of its members, the net work done on the system equals the change in kinetic energy of the system. So you're going to see that whenever an object moves, it's moving due to some kinetic energy. It has kinetic energy so that it can move. And the word kinetic means that, right? Kinetics, kinematics, it means motion. So all of this we've studied kind of along the horizontal, right? So we now want to use this definition and go a step further and say, what about when an object is about to move or ready to move? Right before it has that kinetic energy, what does it have? Any guesses?
Potential energy.
Oh, yeah, I saw lots of people unmuting. I just saw a whole bunch of people unmuting. Yeah, right before it has kinetic energy, it has the potential to have kinetic energy. And we can study that by now flipping our horizontal axis to our vertical axis. And that's our last step here. So here, oh, I see a comment. Mitochondria is the powerhouse of the cell. Yeah, we're gonna give that to them. People.
I'm just joking. I'm sorry.
I need to not say anything about chemistry people anymore. Okay, so let's flip our object and flip our situation to a vertical scenario now. Here you have your favorite physics book, and it's going to be placed in some position along the vertical. And this position we're going to call y initial. Using our free body diagram, we know that the force of gravity is always acting on this. We are going to use use some applied force to move this book up. As you move this book up, it's going to move some displacement R here. Then its final position will be called Y sub F, of course. Final position will be seen, you'll have it here. And so now we could look at what is it that we've exactly done here. And as always, you can start with all of your vectors and then pull in what you know from our Newton's second law. So our displacement vector is y final minus y initial, that's the magnitude of it, in the j hat direction. So we can look at our definition for the external work done on a system, and we say F dot dr. In this case, we're going to say F applied. F applied is what causes that displacement, which means that we have some work. If we then do Newton's laws of motion, right, I'll do it here somewhere. The sum of the forces in the y here are going to equal, what do we have? F applied minus mg. And here, once we get to this position, once we get to that position, there is no more motion. So we are static in that position, and we make this equal to 0. So the F applied here is equal to mg. If you're not convinced by that static position of the book at the end there, you could also relate to yourself that the two move together, right? The force of gravity will always be there, and as you're applying a force, the two will vary with each other, almost like opposites. Okay, so our magnitude for F applied then is mg, and this is in the j hat direction. Our displacement vector is final minus initial in the j hat direction, and so we do the dot product of j dot j, and we know that that is equal to 1. And so our vector notation goes away. We're done with that. And so we're left with mg y final after we distribute times mg minus mg y initial. And so here now is your definition for potential energy due to gravity. So this is the gravitational potential energy, and that's why you see this little g here. This is potential energy U. Sometimes you'll also see it as potential energy PE, like that. And this is the change in work done on a system, and this system, the force applied is opposing gravity or due to gravity. Do I have anything to out that here? Yeah. So while the book then was at its highest point, the system had potential to possess kinetic energy. So if you're at the highest point and the book is not moving, it has potential energy. As it starts to drop, every bit of that potential energy converts to kinetic energy. So at your highest point here, you have a really high potential energy and a very low kinetic energy because you're not moving, you're static, you're still. As you fall down to the ground, and let's say this position here right before you're falling, you have a very low potential energy because your change in y is now really small, and you have a really high kinetic energy because your velocity has increased. So these two vary with each other. I think I have one more statement. So the energy storage mechanism before the book is released is called potential energy. And these two kind of work hand in hand. And you can have other types of potential energy. It doesn't have to just be from gravity. Yeah, like putting gas in your car, that's a type of potential energy. You're storing energy. Holding the spring back like that, the spring has the potential to move, but it doesn't quite yet. And so here, or food. Oh, and that's a great one because that's chemical potential energy. You putting food into your system so that you can then exert some sort of work, right? Some sort of kinetic energy to move. Yeah. Okay, so this is gravitational potential energy, and it depends only on the vertical height above the surface. The mass is, inherent to the object, gravity exists. And so the only thing that changes here is y. The higher your y is, the more potential energy you have. And in fact, you'll have more kinetic energy as you're falling. is G negative still? G, as when you put this into yes, I'll just say yes. G is the value, G is negative. So if mass were 5 kilograms, right? If mass were 5, so I'm just going to show you where the negative came from, because I really want you guys to get this. When we put in, notice that the negative of mg is right here, and that's where that negative sign was in there, right? So the negative is always there, and the negative distributes all the way out. So when you put in your value here, you're going to put in g equals 9.8 because you've already accounted for that value. Now, depending on how you set up your y's usually might come out negative, right? But the point is here that your potential energy is not usually a negative value. Your potential energy is something that you have. If you had negative potential energy, it would only be directional, like if you flip things around. Okay. Oh, okay. Yeah. Okay, great. Yeah, G is, when I'm answering the question, I mean, you're going to put in the value of G as positive, but in physics, G is always negative, but the negative we accounted for already, and that's distributed through the math. Okay, any other questions about this? And thanks Owen for yeah, getting there. Okay, I see Isla, it's good too. Okay, well, that's the end of chapter 7. Yeah, we have formalized work as a mechanism of energy. And the actual energy is called kinetic energy and potential energy. In Physics 102, you will learn about the third type of energy, which is internal energy. But for now, we'll stop there. Should we take like a 10-minute break before we go through, or are we? Yeah, I think we'll take a 10-minute break. How about 13 minutes and we come back at 11:10 and we'll start on chapter 8 and then see if we can get to the lab. All right, y'all. 11:13, everyone come back, go stretch your legs. 11:13. welcome back. I hope I hope most of you are back. I think hi Daniela. I think our coffee maker Nathan is not back. Hi Robin. Hi Gary. Hello Keon. You're all back. I'm glad. Hi Saja. Um, okay, so I hope you had a quick break to move around a little bit, or get ready for like, another hour. I think we could do it. Our goal now for the rest of this hour is to finish chapter 8, and I'm going to set my little timer so that we can stay on track here. Okay. So everything we've done so far is trying to figure out what is energy, right? And how is it that we get energy even into a system? And so that's what our next goal is to think of how energy comes into a system and how we can study it if we isolate a system and really just work with what we know. Because sometimes if you don't know enough of a situation, if you don't know enough about a situation, then you can isolate the situation to what you do know. Yeah. Do you guys see my large PowerPoint? Yeah. Okay, great. Okay, good. Thank you guys. Yeah. Those of you on the video, your quick reactions really helped me a lot. So thank you for having your video on. Okay. So chapter 8 is all about conservation of energy, and we'll talk about how it's conserved and how we calculate that mathematically, how things come into a system and out of a system. So for anything, of course, we want to transfer energy into a device for it to operate. So when you guys see this, what is this called? Not a hand saw, a table saw. I think I got it. A table saw of some sort. We know that for it to move its blades around, we need to plug it into a wall. And when you plug it into a wall, electrons are now allowed to move through that wall, through the plug, into the wire, and is converted into a mechanical energy. Some motion is a result of that electrical energy. And so that is really a transfer from one type of energy into another, so that we're able to get some motion out of these blades. And you'll see this for everything that you do that has to do with electronics, or even like I think Owen said it, when we eat food, that has to go through a process in our bodies for us to have energy from that food. And so really we're going to look at ways that energy can transfer into or out of a system and then transform within that system. And what all of these small cases that we've been describing are really a form of transferring energy from one type to another type. And so we'll call those transfer mechanisms. And you'll see that there's quite a few that we can describe. Okay, the way that we start with defining the energy of a system is by defining what is the boundary of that system, what's going to come in or out of it. So our first type of system is called a non-isolated system. This is free for all. It is not isolated. Everything and anything can come into it, right? Any type of energy here can cross the border of a non-isolated system during whatever time interval you're describing and interact then with that environment, or it interacts, right? So non-isolated system means that energy can cross the boundary that is established of the system, and interaction will happen. This interaction usually happens because of the type of force or the type of energy that's coming through. For example, if a car is driving down the freeway, you might hear it. If you put your hand anywhere on the car as it's moving, you'll feel that it's hot. You'll see the car actually displacing, it's moving, right? So all of these things are happening because it's interacting with its environment. We know friction occurs because of the tire touching the concrete. And so it's interacting there with its environment, and anything can come in or out of that system because it's allowed to cross the boundary of the actual car frame that we come up with as our boundary. And I'll show you what I mean by boundaries in a second. We're actually going to draw like a circle or a square. And of course, in a few slides, you'll see the opposite. If a system does not interact with its environment, then we can call that an isolated system. And it's up to us how we want to define it. If it helps to define an isolated system because we can remove a lot of unknowns, then we will usually do that. So you'll see that in a few slides. So for now, let's look at what are the transfer energy mechanisms that we are familiar with and that we can now apply some sort of math symbol to, or a variable of some sort. The first type of energy transfer mechanism is the one that we did throughout chapter 7. That's work, right? Energy is transferred to this block here because we are doing work on the system. And we usually write this as a W of some sort. Another type of transfer mechanism, energy that leaves the radio from the speaker. When we hear some sort of sound, this is a mechanical wave that's leaving the system. So it goes from some electrical energy and then transforms into something that we can hear as a sound. So this is a mechanical wave, and this is the same type of mechanical waves you would see in the ocean or when there's an earthquake. Anyone in the South Bay? There was a small earthquake this morning. So those type of...
I felt one. I swear I felt one. And I was like, no, there's something else that happened, but like nothing else could move my bed, you know?
Are you in kind of close?
I'm in like downtown, but like I swear I felt it.
Yeah, my mom texted right away.
And then it like went for a while afterward too. Like it was like, I was like, the bed's still vibrating a little bit. Like at first it was like an initial jerk, and then it was like, just I could see my laptop shaking, but it was like for a good like 30 seconds.
Yeah, and what you're feeling is that last little bit of that wave and the wave changing sizes, because it's an actual physical wave that has an amplitude to it and a frequency, right? That frequency gets lower and lower as we as the earthquake happens.
Does like that friction peak like it does on, you know, like when you go from moving to not moving, like static to kinetic? Does it like peak like it does for those surfaces we're seeing? So like, is that why initially it's hard and then it like, you know, you just feel the shaking?
Yeah, I think so, because that peak is the max amplitude that you're going to see. Yeah.
Oh.
Okay, so MW is what we use for mechanical waves to describe something like that. Ocean, earthquakes, the sound that we hear coming is an actual wave that we're hearing. Another type of transfer mechanism is heat. So here, energy is transferring to the handle by the spoon, or to the handle of the spoon by heat. Here, the water, the tea, or whatever, the coffee that's in here is hot, and the heat that we get is due to constant collision of atoms. So that collision is going to have an effect. It's a what's that? One affects the other. What's that? Collision effect? Is that what it's called? I don't know, but
Cascading.
It's like a cascading effect, yeah, where one thing is, the one hits the other and then they just keep going. That collision continues to grow, right? Like a domino effect. Yeah. Oh, Nathan's back. I hope you have some coffee, Nathan. Yeah, it's a collision process. So everything that's colliding at the bottom of the spoon is going to transfer its way through a collision process all the way up the handle. And this is why you feel heat at the bottom of the spoon work its way up the handle of the spoon. But this is a transfer of heat. Usually when we say energy from heat, we use the letter Q. You'll see this a lot in Physics 102 in the first 4 weeks. Not really that much right now, but we just want to know that when we talk about heat, we know that heat is a collision process that's kind of transferring through, traveling through the system. And this is our letter Q. Okay, another form of a transfer mechanism is when we actually move some sort of matter and transfer it to another body to store that energy there. So energy enters the automobile gas tank by matter transfer. And so we usually call this MT. So here, this matter is being transferred from one area to the other. And this is also how you have convection ovens that work, or the warm air from your furnace, and sometimes from heaters. The warm air is traveling through, right? It's actually moving from one location to another. So this is another form of getting energy. Here we're getting some sort of potential energy, right? Any guesses to what two we haven't discussed yet? Ideas?
Magnetic.
We're along the lines. Oh, Bradley says nuclear. You're all in the right realm of things. Chemical, yeah, we're getting there. At the heart of what you guys are describing is electrical interactions. Yes, so Bradley and Azure, yeah, radiation. And Noah says geothermal, which is another type of heat and mechanical waves. So everything that we're going to describe can be broken down to what's here. Okay, and Nathan has a question. What's the difference between matter transfer and work since something is working to move the gas? Yeah, so Nathan, you bring up a really good situation where you have to break up the time interval and the system that you're describing. So we definitely used our hand and we did work with our hand to move the gas over. But the gas itself, if we isolate the system to just be the gas is a form of matter transfer that is going to sit as potential energy. But my hand did do work to get the gas in there. So it really becomes very particular about the system and the time interval that you're going to identify and the object. Yes, the bounds in the gasoline. That's right. The boundary here of the system is the boundary of the gasoline. Oh, the bonds. Not the bonds. Yeah, not the gasoline itself. The gasoline itself is the system here, and moving this amount of gasoline is we're moving that transfer over. The thing that's doing work here though is your hand. Right? The gas doesn't know it's moving. The gas just sits and is there, and it's going to change positions. But the thing that's moving the position and applying the force here is your hand. Okay, so you guys did get the last two, going along to electrical and radiation process. So the first of the last two is electrical transmission. Energy enters the hairdryer by electrical transmission. And here you actually have electrons moving, right? Moving from the wall, the plug in the wall. Yeah, the plug in the wall, which somehow is wired back to a power plant somewhere. Well, probably to a transformer station first, and then the power plant. And then the power plant, Physics 102, it's all there too, the generators and how we're going to get that electrical movement. So electrical transmission here will be called ET, electrons actually moving. And then our last one is the one you guys came up with, which is electromagnetic radiation, like light that's leaving a light bulb. So any type of colors that you see or any type of waves that you see. Yeah, phone home. Yeah, any type of light, microwaves being used, radio waves that are traveling through space, that is also a type of electromagnetic radiation. The way you interpret this might turn into something else. For example, if you see the light from a bulb and you put your hand near that bulb, you might feel heat then coming from the light. But that heat is a process of how your hand is feeling the particles around it. The thing that's actually leaving the light, though, is electromagnetic radiation. And so here we call this one ER.
Is the heat like a loss in that transformation?
Usually heat is a loss, but it's very specific about heat is very, it's very much based on direction, right? So heat is usually a loss from something like the light bulb, but then we feel the heat as a positive on our hand. So that change in temperature is what you're feeling, and what we will see is actually heat. Most of these are actually, again, based on perspective, a loss, right? It's based on how you look at it. But if you're looking at it from a neutral perspective, it's a transfer of energy and a transfer mechanism. How is that energy allowed to change from one thing to the other? Now, what we know, even in a non-isolated system, which is, the entire universe, that the rule will still stay true, that we can neither create nor destroy energy. Energy will always be conserved. So if we look at the entire universe at the entire universe and the energy that was created in the beginning, we can sum up the entire energy of the universe and call that the system. And we can sum up every single transfer mechanism that's happening in the entire universe. And that'll be represented with this equation, because energy, no matter what, is still conserved if the universe is the whole system, right? So in your system here, this energy will always be conserved. So it means that no changes will happen. The total change of energy of the system will be due to whatever transfer mechanisms happening in the system, and we add each one of them up. If we add them all up, you'll get the total sum of the energy that you started with in that system. So let me show you again. So yeah, underlining the system. So all methods of energy storage will then equal all the possible energy transfer mechanisms that are available. And so to write this equation out explicitly lets you identify each variable and mathematically be able to put something in. So this is what the energy conservation equation looks like explicitly. All of the energy, changes of energy in the system, all those changes of energy can be due to kinetic energy, potential energy, or internal energy. And all of those changes of energy in the system are all due to the sum of work, heat, mechanical waves. This is transfer of mechanical waves, the transfer of matter transfer, the transfer of what is this, electrical transmission, and the transfer of electromagnetic radiation. And this would be total description of the system. And then you go in and figure out which ones actually apply to the system, because there might not be potential energy or there might not be kinetic energy, but this as a whole describes everything that's happening in the universe at once. And again, for example, if the only change in the system is the speed of one or more of its members or one or more of its components, this equation will reduce down to the change in kinetic energy equals work. This is the kinetic energy theorem. So what this is saying is if there was only change in velocity, there's no velocity included in heat here. There's nothing included in mechanical waves and matter transfer, energy transfer, or electromagnetic radiation. This was electrical transmission. And there's no internal energy or potential energy. And so this equation would reduce down to change in kinetic equals work. So we really want to practice identifying the system and identifying what is the boundary that we have. Okay, before we continue with this equation, let's try identifying isolated systems and non-isolated systems and the forces that come in or out of it. So let's try this problem. Before you answer, let us take a moment with it. Consider a block that's sliding over a horizontal surface with friction. Ignore any sound the sliding might make. Okay, if the system is the block, is this system isolated, non-isolated, or impossible to determine? So let me draw it first. So we have a horizontal surface and we have a block. Now, this is the situation. And now I'm going to draw the free body diagram. And here, they're asking us to identify the block as the system. So I'm going to draw the block here and the forces acting on the block. First, we know there's a force of gravity that's always on the block. We know there's a normal force. And I think they said friction, right? And if the block is accelerating or moving with some velocity that way, then we'll say the friction is this way. Do we all agree so far? Is there anything more we should add? Okay. So now let's look. Anyone?
It's an isolated system.
let's keep working on it. Well, we yeah, I got scared too. Sorry, I get razzled and I I need a moment. Okay. Okay. So now we want to look at this block and we want to decide if it's isolated or non-isolated. You want to think if all of these forces acting on the block are, and only the block. Now let me create the system. Let's draw the system is the block. So I'm going to draw a boundary around the block. And you guys tell me, are any of these forces due to outside of the block as a system? Are any of these forces due to environment?
Yes.
All right, name one.
The gravity and then also the friction.
Yeah, I hear gravity and friction from Randy, and Isla says the same thing. Also the
And
friction.
normal, I guess.
Yeah, and the normal because it's due to contact of the surface, right? So if we look at the system and consider the system to be the block, then we have to say here that our system is non-isolated because external factors from its environment are acting on it. Let's try this again now and look at the surface as the system. So I'm going to take a second. If you guys can really quickly flip your free body diagram to the object being the surface, you can also draw this out quickly, but I can draw it out too. So now we're going to look at the surface. This is touching. So now this dot now represents the surface, right? So the surface here is going to be in contact with the block, and so the normal force is from the block acting down on it. Right? This is in contact here. Because we're looking at what's acting on the surface. Is the force of gravity acting on the surface? Ideas. Is the force of gravity acting on the surface of Earth?
Yes.
Yes, yes. It's okay, guys. Our rules have not changed. Our force of gravity is acting on here. Does the surface also feel this friction? The answer here is yes. The answer here is yes, because the friction is due to contact. The friction is due to contact from this block. So we should still have a frictional force there. We have a normal force, Henry, because a normal force is defined as a force whenever there is contact. If there is contact in either direction, there's a normal force acting. So you want to decide what is the perspective here. So the block is in contact with the surface, and so the surface is going to feel a normal force acting back on it from the block. You could call it an applied force too, or the weight force. Yeah, we could also call this the weight. That's probably a better one. Yeah, that's true, Nathan. Yeah. Okay, so then again here, now we're going to look at our system as just the surface and isolate the system. And now we can say, you guys tell me, are any of these forces acting from outside of the environment of the surface? Is this an isolated or non-isolated system?
What does isolated mean?
Isolated means that nothing outside of this blue box is acting on the surface. Non-isolated means that some force outside.
Non-isolated.
Yeah. Okay, yeah, I hear non-isolated. I see from Daniela, Henry, Mehmet, and Amir that, yeah, this again would be another non-isolated system. Let's take another look at the same situation, but now we will consider the block and the surface. So if we draw the block and I draw the surface, we can look at the two free body diagrams that we saw on the last situation, and I don't know, it was a whole bunch of them. So let me just draw the main ones. All right, this is the block and the surface was at least FG. At least we can say also the weight of the thing and the frictional. So now the system is the block and the surface. I need another color. Now the system is everything described. Now is the system isolated or non-isolated? if we consider everything the system, then yeah, I see some responses from Amir and Nathan. Yeah, as soon as we bring in the entire situation into the system, now everything that's acting due to the block or the surface forces, right, will be in the system itself. So that system becomes isolated. So it really depends on what is the object and what is the point of view. You can see that in 3 different scenarios here, the system changes from isolated to non-isolated. This is what you want to imagine. For a non-isolated system, all of the changes in energy in the system will be accounted for by adding up all of the transfer mechanisms. So all of the kinetic potential or internal energy is due to any amount of work, heat, or any of these transfer mechanisms that's being done. What this means as far as the boundary goes is that you have this system boundary and things are allowed to move in and out to affect the energy of the system. And the way it affects it, can be added up, and that'll be the total change of the system. So if the system's change in energy goes down, it will be due to all of these transfer mechanisms and whatever is added up or taken away here. But a non-isolated system means you are allowed to cross this boundary here. The boundary here has been crossed. We were okay there? I think?
Mhm.
Okay. Okay, so again, this is very important to think about what is the timing of the situation, what is the system itself. So when you're looking at this conservation of energy equation, the entire thing with the 3 energies and the 6 transfer mechanisms, you want to look at the scenario that's given and start to cross things out from what you have. So here's a good process to follow. First, define the system. Then identify the beginning and end of the time interval. Identify the initial and final configurations of the system. So things like what's changing in the system, like a position or an extension of a spring. And then assign the appropriate reference values that you need. You'll see this a little more common when we do a problem. And then finally, write the energy conservation equation completely, and then eliminate or set some terms equal to 0 that do not apply to the situation. So let us try this for this problem here. Consider this following example, and for each example, the system is provided to you, and the time interval is from before the device is turned on. Oh God. Can you guys still see my screen?
Yeah.
Yeah. Oh, okay.
Yeah.
I had a whole bunch of flash windows pop up. I gotta uninstall, but yeah. Anyway, okay, I'm back. Okay, so oh my goodness, I'm back. So the time interval is from before the device is turned on until it has been operating for a few moments. In this scenario, the system is defined as the television set. The system is defined as a television set. The time interval is from before we turn on the TV to after we've turned on the TV and watched it for a few seconds, a minute or so. So our next step here is so we did step 1 and step 2, right? Step 1 was define the system, the TV. Step 2 was define the time interval. Now we can look at what is the system and our equation. So we look here and we write out the entire conservation of energy for the conservation of energy equation. And now we think about what is the configuration of the TV set. Is the TV set at all going to change position while it's off to while it's on?
No.
No, correct. So we can eliminate this. Is the TV set, if it doesn't have a change in position, is it going to have potential energy?
No.
It doesn't. Remember, if this confuses you, you can always jump to our definition for gravitational potential energy, and you can see that the height is what matters here. The change in position. No change in position means no potential energy here. The next thing is, are things happening internal to the system, like, I don't know, maybe a change in temperature or electrons moving through it?
Yeah.
Yeah, there's something happening there. Yeah, I see you guys in the chat too. Perfect. So now we can start eliminating things. And the first one is because you eliminated the change in kinetic energy, it's a good sign to eliminate the work. Do we feel heat coming from the TV set when it's turned on?
Yeah.
Yeah. Yeah.
We used to. No, not anymore, really.
Well,
Do they? Do they still emit
Yes.
heat? Do you think? Probably a little bit.
Very
Mhm.
little.
yeah.
Because they're more efficient, like the light bulbs. You know, like an
Very
incandescent versus an LED, the heat is much less.
Yeah, very little is still something. And you probably, if you felt the inside of your electronics, you would probably feel the heat there. But very good point, guys. And we'll get to that. We'll get to that physics 102, the amount of heat and efficiency. You're probably going to hate it in physics 102, but we'll still get there. Okay, what about what is this? MW, mechanical waves. Do we hear sounds? That's a quick one. Sound.
No moving parts.
But do we hear sound? Sound is a mechanical wave.
We have sound from the TV.
That's right. And the television set is the system. So we do have mechanical
Oh,
waves.
so we do have moving parts because the speakers move.
Well, a mechanical wave isn't necessarily a physical moving part. It's a
Oh,
physical thing. It's a wave. A wave. Right? A wave. A wave.
So that could be the light and the sound.
Yeah, that's right. So let us actually, yeah, let us mechanical wave can be light also. So we'll say that one too. What about
Could it be like the UHF wave, like you pick up from the, you know, like from the air?
Yeah, it could be that. Yeah. What about matter transfer? Do we see anything of matter transfer?
Not yet.
What is it?
I said not yet.
Oh, not yet. Okay, great. So
Soon.
that's no. And what about electrical transmission? Electrical transmission. Yeah, we see that. Yeah. Okay, I see it in the chat too. And so your equation should reduce down with the description. So think about it. Your television set is a non-isolated system. It warms up after it's turned on. It takes in energy by electricity in order to operate. And it emits energy by sound from the speakers, light from the screen, and heat from those warm surfaces. So this equation reduces down to this. Did we get it all right? Yay, we did. Now, of course, there's going to be little bits of interpretation here. And like you guys said, something about the efficiency. Yeah, that can change. All of those situations can change, but that must be included in the definition of your system. There's another one of, there's two more of these. Yeah, when you were a kid, televisions were far warmer. I was going to say the same thing.
They weighed a lot more.
I was going to say one of my television sets, I had to walk up to it and pull the knob to turn it on. So I could argue some type of work being done there. But again, details. So you have another two of these that you can practice in the you can practice at home. And I'm going to just do the last one just because this one, I don't know, this one's good situation to really think about what is the object and what is the system. So here the system is a cup of tea being warmed in a microwave oven. A cup of tea being warmed in a microwave oven. Now, let us say that this is one of those older microwave ovens that does not spin. There isn't, yeah, that usually comes up. So is the cup of tea in a standard microwave oven, like the ones you would see at school, right? The ones that don't move. Is the cup of tea changing position at all?
No.
No, it's not. Yeah, it's not changing position and it's not changing height of any sort. So we can say that there's no potential energy there, not even a chemical one. Yeah, there were microwaves that don't spin. It's totally true. Yeah. If you were ever at Trade Tech, and I'm sure some of you were not, but if you were, the science building is one of the older buildings. And everything in the building is on the older side, including our microwaves. So Yeah, they won't spin, but that's okay. That's okay. Okay, so is there anything internally happening to the cup of tea as it's being warmed in the microwave oven? Yeah,
No.
a lot is
Oh.
happening internally. Well, it's going to heat up, right? So we know it's going to heat up, and that's our first one. Heat Q will happen. There's no work being done on it because we said no change in kinetic energy. Henry's doesn't spin. Henry, just FYI, if you have a microwave that doesn't spin, you can do a lot of cool physics with a standing wave in the microwave. Yeah, it's pretty cool. Let's see. Is there any type of mechanical wave that's affecting this cup of tea?
Yes.
What is it?
Microwave.
Microwave is electromagnetic radiation.
Oh.
Yeah. The mechanical
The
wave.
fan?
Yeah, a fan is in the microwave, but it's not the cup of tea. But it is the microwave. So you're right that it's acting on it, but we want to focus on the cup of tea. Plasma grapes, and throw some grapes in there. No. Okay, so if we think, oh, okay, here comes another one from Nathan. Possibly heating the tea makes it boil, so that causes the surface of the water in the tea to move waves. You know, Nathan, that's true, and that would make waves in the water. You're right there, but we don't see the word boil yet. We just see warm, so we wouldn't go as far as saying that. But if this said boiling, you could say there was motion there. So we have heat and we have electrical radiation. And I think actually those are the only two that count here because there's no matter transfer when you're looking at the cup of tea because the tea is already made, right? The water was already put into the cup and we're looking beyond that situation. The electrical transmission here happens to the microwave oven. It doesn't actually happen to the cup of tea, but I could see that you could argue that. But the majority of the energy or the transfer mechanisms here is going to be heat and electrical radiation. So this cup of tea, a non-isolated system, will increase in temperature. So the input of energy here is by electromagnetic radiation, which is those microwaves. And the heat term represents some energy transferring out of the hot tea into the lower temperature. The reason we're able to feel hot is because it's how our skin interprets the particles that are leaving from the change in temperature that we feel from the cup to our skin, the air surrounding the cup. And so here, your equation does reduce down to just this. If we were to include the microwave oven as part of the system itself, like the entire system, this would change. This would definitely change. So again, it's really important to identify what is it that we're studying. And here it's the cup of tea and what the cup of tea is going through. Okay, so this is everything for a non-isolated system. For a non-isolated system, the change in energy, first, the change in energy will occur, and the change in energy will be due to all of the transfer mechanisms that are at play. The opposite of this situation is an isolated system where no change of energy is happening that will cross the boundary. Nothing will cross the boundary to cause a change in energy. The energy might vary between kinetic and potential, but it's not going to change because of, it's not going to increase or decrease in total. The change of energy will remain zero. So here you have the scenario where no energy crosses the system boundary by any method. And so here you could say that the sum of the changes of energy are those that are stored in the system, and you have the change in kinetic plus the change in potential equals zero. This is what an isolated system means, that there is no change in the system. So the sum of changes of energy stored in the system will not change, and there are no transfers of energy of any kind across the boundary of the system. Instead, they're going to happen within the system. So we'll see a definition for this. Notice that we don't have internal energy in here because internal energy is just that, internal to the process, and will not affect anything in the environment or in the boundary, out of the boundary. So that's not included here. So writing this non-isolated energy here, writing this isolated energy where there is no change in the energy of the system, this is what we call mechanical energy. So this will work for this isolated system. And here, energy is not transferred across the boundary of this isolated system. It is instead transformed within the system from one type to another. And the transformation mechanism, for example, if we look at this system here of just the book falling, we start with really high potential energy here, right? And really low kinetic energy up here. And all of these two switch places as we get lower and lower, the potential energy will be less and the kinetic energy will be more. Oh, that was supposed to be up, sorry. that will start increasing until we finally get to the very bottom where now we only have kinetic energy. All of the kinetic energy is increased and there is no potential energy or no arrow at all. So here in this isolated system of the book falling, you see the transfer of energy happen within the system of the book falling. And a question, does this only apply when the book is in the air? When the book is in the air and it falls and hits the ground, right? When the book is, oh, I see what you're saying. When it's moving within the air. Yeah. You could even call it to when it hits the ground. Yeah, you could call it to when it hits the ground. The point is that its change in height is what's changing here, right? The potential has a very high height, and that gives it a high potential. And as you reduce the height, the potential energy reduces, but the velocity increases, so the kinetic energy increases. So the two move with each other. Yeah, so when we are looking at just the motion of objects, this is what we call mechanical energy. So this is the conservation of mechanical energy, what we just described. It's defined as the kinetic energy plus the potential energy. That's mechanical energy is defined as kinetic plus potential. It's just a different combination that we're naming here. So the sum of kinetic and potential energies of the system is the mechanical energy, and this potential energy includes all types of potential, including gravitational, chemical, potential energy from a spring, any other place like that. So the conservation, though, of mechanical energy means that there's no changes. So the change in mechanical energy is equal to 0 for an isolated system where the quantities are conserved. So conservation means that there is no change in the system. The total and the final and initial scenarios are the same, or total equal the same, but the way that they change in between is all within the system. So if you start off with, I'll just give you an example, like if the potential energy is 10 joules for the book at the top, as it's reducing down, right, it could change to 9 joules, but now the kinetic energy has become 1 joule. So you see that the change here is 0. There is still 10 joules of energy that we started out with. And as you reduce down, eventually your kinetic energy will become 10 and the potential will become 0. So there's a transfer there. Okay, so for us to use this equation in a problem, you want to write the changes in energy explicitly, meaning you want to write out every single step. So this is the change in kinetic plus the change in potential is equal to 0. Change in kinetic, final minus initial, plus the change in potential are equal to 0. Then you can rearrange this in the equation to put all of the final terms on one side and all of the initial terms on the other side. And then you can write those equations explicitly. So 1/2 mv squared final, mgy final, and that is equal to the initial components. And finally, then you could also write this as the full energy equation, right? So the mechanical energy plus internal, remember this is kinetic plus potential. Mechanical energy plus internal energy equals your total initial energy, which is equal to your total final energy. So this here is the change in energy final equals energy initial. And this is very useful for solving problems. Today and tomorrow you'll see that setting the final and initials equal to each other can be very helpful. Yeah, so the change in energy of the system in total is equal to 0. And we have a lot of components to work with there. Yeah, and so this is what it looks like when we use that boundary. The system of the boundary here contains the kinetic and potential and internal energy, and nothing is allowed to transfer in or out of it. Nothing is allowed to cross this boundary here because it's an isolated system. So the changes happen within, right? These transfer within each other. So the change in the energy of the system is equal to 0. How are we doing so far? Y'all awake up there? Or okay? All right.
So it's like more about the perspective at which you're looking at the system?
Yeah, that's absolutely right. And usually in the beginning, the early problems that we'll do, they'll usually tell you, they'll try to tell you, but eventually you have to get very almost literal with how you read a problem. And we have to eliminate all the small details that we think of so that you can get the perspective right. Let's try a problem with that perspective in mind. Okay, here you have a ball of mass m is dropped from a height h above the ground as shown in the figure. Neglecting air resistance, determine the speed of the ball when it is at a height y above the ground. Choose the system as the ball and the earth. Choose the system as the ball and the earth. Okay, so we can think of gravity and things like that in here. So here's our situation. We have a person that's going to let go of the ball, and the ball is dropped then from some height h. This is our height h. Then the ball is going to be at any other distance y from the ground. We want to figure out what is its velocity. Okay, and the velocity here is pointed down, and the final velocity could be anywhere distance y that you choose. Okay, so when we look at the initial situation, we can write as much as we know. So for the initial situation, the initial height is h. Notice the initial height is h. The initial potential energy is mgh. H is our y here. mgh, y initial is h. Our kinetic energy is 0 because the velocity here is 0 until the ball starts moving. So no kinetic energy. Then we look at some later time, and we call that our final. And this could be any moment in time, wherever we decide. The final position of y, we're going to call it y here. So this is y. The final potential energy will be mg y final, and y final here is y. And because we don't know if it's fallen yet to the ground, so it still has potential energy. We know y is greater than 0. And the final kinetic energy at this point where we measure it is 1/2 mv squared. And this is the final velocity here. And again, this final is really based on our perspective. We're choosing to call this point in this position of this ball here final. And then just to set up your origin, you can have your initial, your zeros here. Okay, so they want us to find the speed of the ball and choose the system as the ball and the earth. So everything, and the ball and the earth is one system. And so we can start with our mechanical energy being conserved. Because the ball and the earth are the system, nothing else is impacting or interacting here. It's really nice when you have the whole system here. That's the entire system. Okay, so let's write this out explicitly, K final minus K initial, right? And plug in everything we know based on our drawing. This is U final minus U initial. So based on our drawing here, we have K final 1/2 mv squared, that's here. K initial is here, equal to 0. And remember, this is what we set up as our initial. And then we have our potential plus our change in potential is final, which is here, minus initial. Initial is here. And so just from the drawing and figuring out our initial configuration and our final configurations, you can set up your equation, and the whole thing is equal to 0 here. And what they wanted us to solve for was this speed. So now it's your turn to rearrange things. So let's see which path they took to get the velocity. So you multiply times 2. Okay, that's fair enough. Wait, you bring everything over to the other side. The masses cancel out. Do you guys see that? We bring all of this over to the other side. And then the masses from the other side cancel out with this mass. And then we bring the 2 over to the other side. And so now we have 2g, which is here, times that change in y. When we bring this over to the other side, there's a minus sign there. That minus is going to flip the y minus h to become h minus y. I'm gonna just do it because this is what happens sometimes. So this is initially y minus h. We distribute the negative sign in, and this becomes then h minus y. And that's where you get h minus y here. And so the final velocity then, we square root it and we get everything we need to know about the velocity in terms of just the change in height. And notice this equation, this h minus y is just the change in height. I'm going to use delta y just because that's traditionally what we say for change in height position, but know that, you know, this y is already being used as a variable in this picture. Ta-da! So there's...
Why does the m cancel in the first thing?
So we brought over this group here to the side, and so you're left.
Okay.
So the m's cancel out there. And it's really nice to see that, again, Galileo's point is proven, right? The speed of something falling does not depend on the mass. It in fact depends on gravity and the height. Ta-da! This is really nice. Okay, I'm gonna flip this on you guys a little bit. So make sure those hats are on. Let us now figure out the speed at that same height y, but now we're going to choose only the ball as the system. We're only looking at the ball, and we're not looking at it falling to the ground, just that it's moving. We cannot say that it's falling, but that it's moving at some speed. So here we do not have the idea of how do we say it, that potential energy, right? We have something moving, so we can say we do have a change in kinetic energy, and we remember back that the change in kinetic energy is work that the ball is doing. So let us write this equation out explicitly too, and this will help us out. So the change in kinetic energy is K final minus K initial. And the work here is F times delta R, right? So K final here is what we drew in our last picture. And let me show you what it looks like in the picture. In this part B that we're doing, now the scenario is just this. Is just this. And so we don't have any potential here. We're only looking at this part, not the ground moving. So that's the difference here. So we say that the ball is moving, so change in kinetic equals work. That's our kinetic energy work theorem. Change in kinetic explicitly then is final minus initial, and our initial here is going to be 0. Work is F times that displacement. So here's our force due to gravity and displacement here. And we write this out not explicitly, we write this out magnitude and in vector form. Fg is equal to minus mg and j hat. delta R is equal to the change in Y. And we'll look again at what our change in Y was. And this is times J hat, and J dot J is equal to 1, so this goes away. So now here, this reduces down to mg delta Y. Mg delta Y then is mg times that negative Y minus H. This is where that negative sign came in from the one before. So if you remember on the slide before, it was H minus Y, and we flipped it around. This is what it was before we did that flip, negative Y minus H. So that stays there. Now we distribute that negative out just like we did on the last slide, and we're back to mg H minus Y, which is the same thing we found on the last slide. And so this whole thing then is equal to our 1/2 mv squared. And we continue solving it, and we solve for that v squared. Again, the masses cancel out. The 2 comes over to the other side, and we square root the whole thing. And look at what we've just done. Based on the perspective of the ball, we get the same exact answer. The velocity of the ball does not change at all. What has to change is your system, and you have to keep that consistent throughout the entire solving of the problems. So based on the ball as a system, you get the same answer as if the Earth and the ball are in the system, but you calculate it 2 different ways. How are we doing out there?
It's rough.
Yeah, I have a little bit of a headache, so I imagine you guys do too. I'm going back for Isla just to see. So the ball in free fall, you can consider the change in the change in mechanical energy, right? Gravity and kinetic. But if you're considering just the ball and only the ball moving, not considering that it's falling and that's its actual motion, but just that it's moving, then you would only look at the change in kinetic energy. This is identical to looking at a ball moving in a horizontal line. You're just moving that system around. Okay, I'm gonna throw one more thing at you guys. And again, if you feel like this is a lot, it is a lot. We're on a 3-day week, and you know, we have to get through this course. It's accelerated. So I think I warned you guys maybe the first week that week 3 was the roughest. Week 3 is the roughest. After this, it'll go back down. Don't worry, guys. Okay, I hope that was enough time, Isla. I hope you got what you needed. Okay, so what we've been doing up until now, okay, good. What we've been doing up until now is looking at energy and energy for a scenario. But as we keep saying, we are people that are interested in exact moments of time and how do things change over time. So the idea of energy can also change over time. And this is where now our power comes in. So we're going to jump to the back of the chapter and look at power. Here, the time rate of energy transfer is called the instantaneous power. Now the derivative of the energy. So looking at energy over time, Everything we've done in this chapter is look at the change in energy. Now we want to see how does the energy change over time, and that'll give us like an average of power. But of course, we are interested in the instantaneous power, right? So this energy that we're looking at could, if it's due to some motion as an average, we could look at it as work, also work that's being done. But it's really any energy. Work as any energy transfer method over time will give us this average power, right? Average power. And this is the work done by some external force on an object in some time interval. And so here's an example of us doing some work. What if we wanted to move this crate up this ramp here? Then you could certainly apply some force, and you would move some displacement. You'd apply some force here. You'd have some displacement, and you'd have some angle theta, and you would produce some work, and it would take you a certain amount of time to complete this job. That is the amount of power that you use, the amount of energy over time to move this crate up. What if then instead, you guys tell me, What if instead this angle were something like this? Oh no, I went off screen. This is a smaller angle theta. If this smaller angle theta, is it gonna take us the same amount of work to get up that ramp? What do you guys think?
No, the displacement will be greater.
Okay, the displacement is greater. Is your force going to change over that displacement?
Yeah, it'll be a little less, I think.
Yeah, so the two will change, but
It'll be
believe,
the same work.
yeah, that's right. So even though there is a change in the force that you have to apply, probably less force because the angle is smaller and the angle is not as steep, then your force is probably a little less, but your displacement is larger. So they'll balance each other out. So believe it or not, the amount of work that you do here is equal to the amount of work that you do here. But what is the thing that changes? Over a short ramp to a long ramp. The thing that changes from a short ramp to a long ramp is the amount of time it takes you to push that up. So what changes is not the amount of work that you put in, but the amount of power that you have to put into the system. And so this power will really tell you a lot about how the energy is distributed over time. So if we look at, we have everything to calculate power. We've done a lot of work with energy and a lot of work. So now we just need to include that time interval, and we pull in all of the calculus that we know here. And we say that if we were to limit that time interval to as close to zero as possible, the definition of power then is just the derivative of that energy, of that work that's being done over some amount of time. Now,
So doing the same amount of work in the same, or doing like more work in the same amount of time would require more power. And
that's right.
Doing like more work in a longer period of time would require
less power.
Less power. Okay.
Yeah, that's right. And so this is one of those situations where you really want to make sure what is it that you're talking about, the amount of work or the rate of work. The rate of work is the power. And so if we want an instantaneous look of what this power is doing, we look at this derivative. And of course we know, okay, Henry says, how is E equal dE equal to dt? Well, remember, how did we get kinetic energy? We derived it from work. So energy here, this amount of work is any external force that does movement on a system is this type of energy. That's just in our definition for what we define as work, and for power, what is it that we define? So here, the work is going to be any energy transfer method, and that's specific to power. This is specific to power. Okay, so here, this work also, we can look at it as our force times our displacement, right? So force times delta R, the derivatives come in here, and you could very easily just plug that in there, and then you will get that the derivative of the work is the force times the derivative of the displacement here over time, because all we're doing is bringing in this delta T down here. And this quantity here, we know as velocity. So power is defined as the force dotted into the velocity. If it's along, the same horizontal, like maximum values, then you can say power equals force times velocity. And to Henry's point, because we can say that energy is equal to any type of work here, or the other way around, the work is any type of energy, here the power is equal to this force times velocity is any type of force that's involved. Any type of force that's involved. And this might give you a clue that you might need Newton's second law at some point, because there might be several forces involved. Okay, and finally our unit then, okay, velocity we know that's displacement, that's where we got this. Our unit for power is the watt. The watt is defined as the joule per second, and this comes straight from the definition, energy over time. right? Energy, I know that's hard to see, but energy over time. The SI unit breaks down to kilogram meter squared per second cubed. And again, break down the joule, Newton meter, break down the Newton, kilogram meter per second squared, and you'll get this answer here. Power is in units of watts, right? You might have also seen horsepower. So 1 horsepower is about 746 watts. You don't really need to know that, not memorized at least. Something else you might have seen in your power bill, right? When they describe a kilowatt hour, this is actually taking a kilowatt and then times an hour, and this is 3.6 times 10 to the 6 joules. Something you'll see too. Nothing that you need to actually know, but just things that we've seen, around every day. Okay, so I've thrown quite a bit of power equations at you, and what you really want to remember is that the power is the energy over time. Power is the rate of energy over time. And we can try one problem, and as soon as we finish that problem, we'll be done. Okay. Okay, everyone, here we go. Let's try one problem. An elevator car has a mass of 1,600 kilograms and is carrying passengers having a combined mass of 200 kilograms. A constant friction force of 4,000 newtons slows its motion. How much power must the motor deliver to lift the elevator car and its passengers at a constant speed of 3 meters per second? So here's the picture. We have an elevator, and the elevator has a mass of 1,600 plus 200. So the total mass here is 1,800 kilograms. Okay, the motion is, you'd like the motion to stay at a constant speed of 3 meters per second. So this is V is equal to 3 meters per second. Can someone tell me what is the acceleration?
0.
That's right. Our acceleration is 0 because we are at a constant speed. And that is how an elevator truly feels until you're changing that speed when you're about to get to your floor, right? And then you feel it in your body. But before that, it's at a constant speed. It also tells us the 4,000 Newton frictional force that's slowing its motion. So this is opposing the motion, and the frictional force is downwards and the motion is upwards. We want to know what is the power in this motor. So the object is the elevator, so the tension is away from the object parallel to the string. And of course, we know the force of gravity acts on this. If that was a little too fast, ask any questions, or I can repeat anything. Let's take it over to the other side and look at the free body diagram for this elevator here. And here it is. The object is the elevator. We have a frictional force slowing it down. We have a gravitational force that's due to the mass and gravity. We have a tension that's pulling it up and acting upwards. And the motion of the elevator is directed upwards also, and that's our positive sign. So here we're all in the y direction. We can do the sum of the forces in the y direction, right? Sum of the forces, then tension minus force minus mg, and is equal to 0 because our acceleration is equal to 0, although we do have a constant speed. And here's where you want to think about what is it that you're doing, right? You want to calculate power. And here you are working in terms of forces, and you're given a velocity. So perhaps we're going to need this equation, right? But what are the forces that we know? We were given friction, we were given mass, and we know gravity. So let's solve this equation for T, because that's the one thing we don't know. So T is equal to mg plus F. And now this is our force. Remember that tension is a force. So we can plug this into our power equation. Force, velocity here, right? And the magnitude, all is in the same direction. So J dot J equals 1. T times V, and this is T, and this is our value for V. And now we can plug everything in. We know all of these numbers. So the total mass is 1,800, gravity is 9.8, the frictional force here, is 4,000, and I'll just leave it alone. Frictional force is 4,000 newtons, and the speed that we want is 3 meters per second. And so our entire problem then here, the power needed for the motor to maintain this constant speed is 6.49 times 10 to the 4th watts.
We calculated the friction with the normal force and the coefficient of friction or something?
No, we were given the frictional force.
Oh.
Yeah, if I'm going too fast, it might be I would just watch, but it's up to you how to catch everything. Any questions about this problem or about power? Okay. Take a deep breath. I know we've done a lot. I feel it too. Henry, can you explain going from equation 2 to 3? This is equation 2. Oh, okay, great. So this is where our Newton's law of forces come in. So the way I would start this problem is by saying I'm trying to solve for power and at a constant speed. So this is the velocity. So I need this force. We don't know this force. When I don't know forces, but I know things are moving like the elevator, this would trigger to me to go to Newton's second law and use my free body diagram. And so we sum up all the forces in Y, and because we know friction and mass, we bring those all together to one side and we solve for the unknown. And our unknown is that force there. That is our force. And now we can apply our force to our power equation. Power is equal to the force times velocity, right? Power equals force times velocity. And our force is this tension right here. And so, yeah, we plug in mg plus f here, and our velocity is carried over. So here, there's 2 steps of physics. But I would probably start here, knowing at this corner here, knowing that I'm being asked to solve for power, and I want it at a constant velocity, so I should use this equation, and I should solve for the unknown forces. Okay, any other questions? Okay, our next topic, just kidding. Just kidding, end of slideshow. Okay, so yeah, take a stretch to move around, do what you gotta do. Can we move on to the lab, or would you guys like a short break? Okay, I got a vote for lab, and oh my God, I can't see all the chats. Oh my God, I can't see them. Oh, everyone says lab. Oh, no, Nate says short break. Okay, I'm gonna go. Okay, swallow the frog. Okay. You guys are saying, okay. For those of you that need a short break, take a moment. Actually, I'm gonna stand up too. While I'm setting up the screens for the lab, move your legs around. I'm moving my desk up. Yes, I see Keon squatting. Okay, I've moved. I'm standing. Yeah, 26 squats. Move things around, get ready. It'll take me a minute to set up the screen, so I'll do that while we, oh my gosh, my legs, how do we do this? Jesus. Yeah, move around, guys. Move around a little bit. My God. Okay, let me, yeah, only 10 squats. Okay, let me put this into, this is totally enough time to go use the bathroom too, if anyone has to go use the bathroom while I set up my screens. Okay, I'm gonna go straight from student view and follow it as if it were as if you guys were seeing it, and we'll just kind of go and hope that it works. Let's see. This one. Okay, you guys should see my screen now, and I think, oh, sorry, I'm moving it around. Hold on. Okay, now you should be able to see it. Let me get my chat window up. I'm going blind now. Okay, and we're gonna keep moving our legs around. Put my pants up. Okay, so our lab for today is called the Energy Skate Park. I think it's pretty fun when you start moving it around, when you start moving all the things around. The first thing to note is that I've made the due date to be the 25th. So take your time reading it, and the 25th is Monday after the exam, so end of Monday. So I suggest you get started on it, at least do the calculations for it. Okay, so again, submit by Monday at midnight. So this lab question?
Yeah, I do have one question on this. Where it says using configurations shown, that's why I was confused.
Okay, so I'll go through it and we'll see where that comes up. So again, submit by Monday. Now this one will have a lab report. So your lab report will include these 3 sections and then the questions in the manual. The 3 sections are only the objective, the conclusion, and the discussion. You can look at the sample report to get an idea of what these sections entail. This is only so you can look at what is an objective, what is the conclusion, and what is the discussion. Notice how they're placed in one page before the actual lab. That's a really good way for me to be able to grade your work. If you place it in a different order, I will still catch it, but there's a little bit more possibility that I might miss it. But usually I don't, but I'd appreciate it if you put those 3 on one page first. So there's one example of conclusion, objective, and discussion. And then there's another example here. I really like this page. I looked at hundreds of these pages. I thought this was the nicer of them all. So you can read through here for examples of an introduction, a discussion, and a conclusion. This might be helpful for your other classes too. Okay, so following these 3 sections, include the responses to the questions as described in the lab manual using the configurations shown. Usually a lab manual will show you parts of the simulation and how it's set up. If it doesn't show it, it's just a carryover from the description of the last lab, but I think this one shows at least one, but let's look. Okay, use the simulation below. I should get rid of that flashlight. Read carefully the whole lab manual to make sure you answer everything. Of course, you can turn it in late. And here's the manual itself. You could do the lab from inside of Canvas, or you can click and let the simulation run on another page. Okay, so let's look at the manual. And this manual is on the longer side, so start the lab. Okay, so this one. Okay, I'll read out loud. Here's an objective. Make it into your own words after you've done this. The objective, to verify the conservation of mechanical energy by really looking at kinetic and potential energies here. The differences between conservative and non-conservative forces aren't something that we're going to focus on too much in this section. If you want to read about it, it's the last 2 sections of this chapter. It really depends on the path taken, but yeah, it's fine. Okay, it gives you a little bit of the theory. Here are now equations that after today we recognize. And here's the procedure. This is the configuration. These are configurations. Okay, so the first one.
Oh, okay. I thought it meant like you wanted the graph shown in our lab report. Some of those lab reports had graphs, and so I thought you wanted us to like put graphs in addition to the questions based on the tables, and like that's what I thought configurations were.
So the first line here says just open the link and then click on the intro graph box. And so you'll see the intro one here, and then click on the quarter skateboard ramp. And this is kind of what the ramp looks like. And you want to click on the menu to show these things, the bar graph, the grid, the speed, and select the smallest mass. And we're going to assign a number value to be 50 kilograms. So let me do this on the other tab. So I click intro, I click bar graph, grid, speed, and I move mass over to the smallest one. And this is, we're gonna give this a value, right? Of 50 kilograms. The quarter, click on quarter skateboard ramp. Where's that? Is that this one? No, it's not this one. Oh, that's here. Oh, okay. Take the time to look through all the buttons. It really is worth your time to look through all the buttons and see what everything does. So I click on this quarter skateboard ramp. I really like this lab a lot. Okay, drag the skater to the top of the track and start the animation. To take in accurate data, yeah, you should have done this. These simulations are used through all levels, but the amount of calculations that you do is where things change, right? Going from average to instantaneous and actual values. And then a question, should we answer the in-lab questions in the discussion portion, the ones in part 1 and 2, not at the end? No, you should answer everything in the lab questions in that part of the manual, and then you can discuss it in the discussion section. And the two are different. The answer and the discussion to get to the answer, different. Okay, so let's do the first step. Drag the skater to the top of the track and start the animation. To take in accurate data, click on slow motion, then pause and play step by step. Record the maximum height at the top of the ramp and the speed of the skater at the bottom of the ramp, and then record this in your table. You can make your own scale on the speedometer, 1 meter per second with a maximum reading of 20. Okay, let's take this guy to the top. Notice, can I just show you guys at the bottom here? Notice the potential bar graph increases as my height increases, and so does the total energy. So at the top here, you can take your data, like what is the height is 6 meters. And then at the bottom, the speed, oh hell. He fell. Okay, at the bottom, the speed, somewhere around there, right? You could put it also in slow motion like they told you to and repeat it. That's what the green button does. And it'll stop right there. So you could count the notches then, the notches as 1 meter per second. 1, 2, 2, 4, 6, 8, 10, 11. That looks like 11 meters per second. So let's go back to the, so you want us to scan and upload the manual as well. The way that you provide the questions and answers is totally up to you. If you want to retype it or answer it in a different doc, totally up to you. As long as I get answers, that's all that matters. Okay, so those two data sets, the two data points we just got would go then right here. So the type of motion is the skateboard ramp. The maximum height was 6 meters. You could now calculate what is your potential energy, mgh. The equation is in the lab manual. Your final speed was 11 meters per second, I think, and now you can calculate your kinetic energy, 1/2 mv squared. And then it looks like the second one will tell you to do the same thing in free fall. Let's go to the top and answer, let's see what it says. Yeah, drag the skater upward to the same vertical height and release it from rest, free fall, and then record the final speed before it hits the ground. So restart the skater, oh my God. Now here he's at free fall, I think that's what they mean. And then just let him drop and you'll get a final speed. I didn't catch the speed. Did you guys catch it? Let's redo. Someone watch it, someone watch it. Oh, that was hard to see. So try to estimate it. Perhaps it gives you values somewhere, but just try to estimate it as best you can. I think it was close to 11 also, somewhere around there. Oh my God. Okay, so calculate the potential energy and the kinetic energy for both cases in the ramp and the free fall, and then compare the results. So now we go back to our table. You would have had a maximum height for the free fall, and you calculate potential energy. You record the final speed for free fall, and you calculate the kinetic energy there. And then you do the same thing, and now you're going to do it for a mass of a skater for 100 kilograms. So you can move over the mass notch, and it'll describe it to you here too. Change the mass of the skater to a large mass, and that'll be 100 kilograms, and repeat it. right? So just change to 100 and repeat. And you'll get the values there and you'll plug it into your table. And then you can answer all the questions following. And this next one is for conservation of mechanical energy. And here, I think it's all kind of the same. We just follow this instructions, go to playground 4, show the grid speed, non-friction, no friction, select a small mass, and again, drag the skater to point A and start measuring the height, and eventually you'll record some speeds at each value, and that'll go in your table. And here's a nice configuration that it shows. I think eventually you make up your own too. And you record the height and the speeds, and you calculate potential and energy and mechanical. It's very similar to the first step that I just showed you. Do you guys have any questions about how to complete this lab? I think it's pretty straightforward.
Supposed to like attach those questions answered on the sheet that they're written on, right?
Any way that you want to provide it, it's up to you. Yeah, it's up to you. The way that is easiest for me to read is if you write on here, it is easier for me to like see it that way. But if you want to rewrite the whole thing, that's okay. I don't mind. Depending on what you're working with, it might be easier to print it or write it or write on top of it. Mehmet, do we have to write our own conclusion, introduction, and procedure, or just answer the questions? So that's at the top. Let's look at the top one more time. These are the only parts in your lab. Nothing else. I know in other classes you learn different, but in this class, your lab report will include only an objective that you write, a conclusion that you write, and a discussion that you write. Following the discussion, which is the 3 parts, then you're going to include the responses to the lab manual. So those 3 sections and then the lab manual. So you do not need to include a procedure of any sort. If you want to just copy and paste the pages, then that's fine. Any questions? Any other questions? Anything to clarify? Okay, I see some thumbs up, some nopes. Okay, I am going to end things here. If you have a question and you are not going to stay, you can email me the question and I'm happy to answer it, especially if you're just not convinced with what I said or need clarification. Please, email me. I'll stick around for a few minutes, though I don't think I can stay very long today just because I already feel my throat going, but you guys can probably hear it too. Yeah, have a good day, guys. I'm going to stay for a few minutes. I'm going to stop recording. Bye. I've never seen everyone leave so fast. Bye, everyone. Bye, Robin. Bye, Andrea. Bye, Amir. Bye, Alexandra. Bye, guys. Bye, Daniela and Saja and Nathan. See you guys all tomorrow. I promise it'll be better tomorrow, or faster and hopefully easier. Oh my gosh, my head hurts. Okay, I'm going to stop recording. Bye, Esmeralda. Thank you.